Hello, today we'll start with Lagrange's mean value theorem, also called LMVT. The LMVT has a few statements. The first one is if y equals f of x is continuous in a comma b. So y is f of x is a function of x and is continuous in a comma b including a and b, hence the closed intervals. And y equals f of x is derivable or differentiable in a comma b, so open intervals, so it might not be differentiable at a comma b. Then we say then if both the above conditions are satisfied, we say a real number c will exist in a comma b such that the first derivative of x at point c, so f dash of c, equals f of b minus f of a upon b minus a. Let us take some examples for LMVT. We need to verify LMVT for f of x equals x cube minus x square minus 5x plus 3 in the domain 0, 4 and f of x equals log x in the domain 1, e. So we take f of x equals this function. Now we see the given function is a polynomial function. A polynomial function is continuous and differentiable everywhere from negative infinity to infinity. Since it's differentiable everywhere, we can say that it will also be differentiable in 0, 4 and continuous in 0, 4, where you are taking open intervals and closed intervals respectively. So both conditions of LMVT are satisfied. Hence we say LMVT states a point C exists in 0, 4 because our range is a, b given by 0, 4 such that f dash of C equals f of b minus f of a upon b minus a. So your f of b equals f of 4. On plugging it into the original equation we get 31. F of a equals f of 0. On plugging it into the original equation we get 3. So then we substitute b and a from here and f of b and f of a as well. We get f dash of c equals 7. Now we know f of x, so then we take the first derivative with respect to x. We get f dash of x equals this, 3x square minus 2x minus 5. But we want it at a real point c. So we substitute x with c. We get 3c square minus 2c minus 5 equals 7, because over here also we have f dash of c is 7 and here we are getting this quadratic equation, so we equate the two. On solving we get this other quadratic equation, 3c square minus 2c minus 12 equals 0, and then we say the value of c will be given by the roots of this equation. So solving using quadratic formula we get 1 plus minus root 37 by 3. So we have got two values for point c. Now 1 minus root 37 is like saying 1 minus 6 upon 6. 1 minus 6 is minus 5 upon 6. So that's a negative value. But our domain is from 0 to 4. So minus 5 by 6 exists outside our domain. Hence we don't consider that point. So we say c equals 1 plus root 37 by 6, which lies between 0, 4. So c is lying between a, b, and hence we say LMVT is verified. Taking the next example of log x in 1, e. Now log x is continuous and differentiable everywhere in the given domain. Log x is non-differentiable at x equals 0 because it becomes negative infinity over there, right? But in the given domain 1 to e, it's continuous and differentiable everywhere. So by LMVT, there will exist a point C where C belongs to 1, e such that f dash of c is f of b minus f of a upon b minus a. Is the same statement as before. We take the value of f of a, f of b, log 1 is 0, log e to the base e is 1. So log a to the base a is 1 as a general property. Taking f of c, we get log c. F dash of c will be 1 by c, derivative of log x is 1 by x. So then we say 1 by c equals 1 minus 0 by e minus 1, just substituting the values. You get 1 by e minus 1. C equals e minus 1. Now our e value is approximately 2.78. We subtract 1 becomes approximately 1.78. 1.78 lies between 1 and 2.78. Hence we say C belongs to the range 1, e, and hence LMVT is verified. Moving on, we'll take the Rolle's theorem, in which we say Rolle's theorem is an extension of LMVT. It has the same first two conditions where it's saying your y is f of x is continuous everywhere in a, b. Y is f of x is differentiable everywhere in a, b. Only difference is Rolle's theorem is applicable where f of a equals f of b. So if all three conditions are true, we say there will exist at least one real number, so there can be more than one as well, where the real number is represented by C, and C lies between A comma B, such that f dash of C is 0. So we know our LMVT formula was f dash of C is f of B minus f of A upon B minus A. Since f of B equals f of A, the numerator becomes 0, so f dash of C becomes 0. That is why this is an extension of LMVT. So taking a few questions. Verify Rolle's theorem for x cube minus 6x square plus 11x minus 6 in 1, 3. So again, this is a polynomial question. So we say a polynomial function is continuous and differentiable everywhere. So it's continuous and differentiable from 1 to 3. Here A is 1, B is 3. We check the value of f of A. We check the value of f of B. Since both f of A and f of B are 0, we can say f of A equals f of B. So all three conditions of Rolle's theorem is satisfied. Hence there will be some point f dash of C where C lies between 1 to 3, such that your f dash of C is 0. So we take this, we have already over here, we take the first derivative, we get 3x square minus 12x plus 11. We take f dash of C, and then using the quadratic formula we simplify, we get 6 plus minus of root 3 by 3. So then this we can test the values, 2 plus minus 1 by root 3. Since both values belong to the domain 1, 3, we say Rolle's theorem is verified. Next question over here is f of x equals 1 minus x minus 1 to the power 2 by 3 on the domain 0, 2. So this we can directly take a derivative of f dash of x, and we see that by chain rule there's a point over here minus 2 by 3, x minus 1, 1 by 3 on solve to the power 1 by 3 on solving, we get this. So for x equals 1, f dash of x is not defined, so it's not differentiable at x equals 1. Looking over here, we have 0, 2. So 1 lies in the domain 0, 2, hence it's not differentiable everywhere. So we say Rolle's theorem is not satisfied over the domain 0, 2 because it's not differentiable everywhere in 0, 2. Moving on to the third question, you can have a general question like this as well. X minus a power m times x minus b power n in a comma b, where m and n are positive integers. So you'll never have a case where this goes to the denominator, and at that point, at say point B or at point A, the function is not differentiable or not defined. So here we say f of x is a product of two polynomial functions, which will always be a polynomial. We can just take a simple example to prove that. 2x plus 1 is x, which gives you a polynomial 2x square plus x. As this is polynomial, as the product of two polynomials is a polynomial, we say this, the product of these two is continuous and differentiable everywhere. So we say f of a equals 0 on putting the values of a in. We say f of b equals 0 on putting the values of b in. So by Rolle's theorem, there will be a point C belonging to a comma b such that f dash of c is 0. We have a value of f of x, so we use f dash of x. Now f dash of x, we need to differentiate using the UV rule of differentiation. The UV rule is u derivative v plus v derivative u. So that's what I'm doing. U derivative of this plus v times derivative of u. Then over here I'll just take this out common, like I'm splitting x minus b to the power n minus 1. I can write it as x minus b to the power n times x minus b to the power minus 1. So from here I'll be taking it out common, I'll be taking these two out common, and I'll get n times x minus b to the power minus 1 plus m times x minus a to the power minus 1. So as f dash of x equals 0 by Rolle's theorem, we say this is 0, as well as this is 0. Since this is a product, since this here is a product, we know that if either one of the terms is 0, the entire product will be 0, hence satisfying Rolle's theorem. So we say either one is 0. Over here we'll get x equals a, we'll get x equals b, which is at the border point, but that's not what we want, because the value c which we should get should lie in between a comma b, excluding a and b, open intervals. So we take the third case, which on simplifying a bit, we'll get the value x equals bm plus an by m plus n. So for the value of the point x equals bm plus an by m plus n, f dash of x is 0. So x belongs in E comma B. Hence we say Rolle's theorem is verified. We can use any variable rather than c. If you don't want to use c or you don't want to use x, you can even take your f dash of p equals f of b minus f of a upon b minus a. So that's why you will see that I have taken x instead of c at some places. Then the last question, log of x square plus ab by x in a plus x times a plus b in a comma b for a is greater than 0 and b is greater than 0. So we are telling a and b both are positive values. So we know log x is continuous everywhere but not differentiable when x equals 0. So as a and b are positive values, this will never be 0. Whatever value you put of x is going to be positive. A times b, or positive into positive is positive. So you will never reach 0 at all. So f of x is continuous and differentiable everywhere in a comma b and a comma b, closed and open intervals. So we take f of a, we get log of 1 which is 0, f of b log of 1 which is 0. We get f of b equals f of a. So by Rolle's theorem we know there will be a point f dash of c where f dash of c, there will be a point c, there will be a point c where f dash of c equals 0. So we take this, we substitute x with c. We take a derivative. On taking a derivative and applying chain rule, over here I've simplified the log a bit, so we'll get 3 different log functions, making it easier for the derivative. But here f dash of c, we take f dash of c, use a chain rule here, use regular log differentiation here, and we say f dash of c is 0 by Rolle's theorem. So this term what we got should be 0. So on taking 1 by c to the other side and simplifying a bit, we get c equals root of ab. Now since c is root of ab, c will always lie in a comma b, and hence we say Rolle's theorem is verified.